Hello, my name is Dan Schaefer. I am Senior Director here at Global Foundries in our Automotive, Industrial, and Multi-Market Business Unit. And I am here today along with Synopsys to talk about our GF22FDX technology and our adaptive body bias capabilities associated with this solution. As part of the agenda today, I'm going to be walking through the benefits of GF's 22FDX technology, our markets we serve, as well as some of the hooks we have in place for adaptive body bias. I'm then going to turn it over to Synopsys, who's going to talk about digital implementation of ABB design, talk about their reference flow that they have in place that ties in with adaptive body bias. And then they're also going to provide a live demo. Global Foundries leads the industry with our 22FDX technology, and the blocks in the middle of this chart highlight the technology benefits that we focus on and see advantages that our customers leverage. The first on the left is the power performance ratio. Our 22FDX, compared to comparable bulk solutions in this node, can achieve up to 50% higher performance or also 70% lower power. This is very critical for customers who are really looking to not only get the performance they need, but also in those standby modes, be able to really throttle that back and put it into a deep sleep mode. Also, 22FDX is going to give you a lot of integration capabilities. So bringing all of those additional blocks into your SoC or system on chip is extremely beneficial to reduce those costs, reduce those area sizes. Time to market, this technology has been in volume production since third quarter of 2019. And finally, from a cost profile standpoint, 22FDX not only provides digital scaling that you would expect in this node, but also with the performance of our FDSOI transistors, we also see substantial analog scaling as well in this solution. So let me jump over to the markets. We are production proven. We are in volume production across all of the markets shown here. On the left, mobile handsets and communication infrastructure. This is specifically tied to 5G millimeter wave and Wi-Fi 6. The best-in-class FT/Fmax of the GF FDSOI technology is what customers are really leveraging to achieve the power that they need at the performance targets. We also support millimeter wave all the way up to 70, 80 gigahertz as well, which is very critical within our PDK. In the consumer wearables and edge IoT devices, this is where customers are using the operating voltage capabilities of this to go down to 0.4 volts. Our SRAMs go down to 0.65 volts. We can achieve 1 picoamp per micron for very ultra low leakage current, comparable to what you see in 40 nanometer design. Industrial IoT, this is where customers are leveraging not only our lower active and standby power from an SRAM standpoint, 1 picoamp per cell, but also leveraging that high density digital and memory. We see customers really leveraging AI in here to optimize in that TOPS per watt in the inference edge space. And then we also in 22FDX supports EMRAM fully qualified, as well as we're bringing RRAM into this technology so you can bring embedded non-volatile memory on chip. And then finally, this is an automotive grade 1 qualified technology. So ADAS radar solutions and in-vehicle infotainment auto MCUs are leveraging, again, the EMRAM, the very low power, and the excellent RF and millimeter wave performance of this technology. So now let me jump over and talk a bit about our PDKs, or our process design kits. Our process design kits are fully enabled with body bias capability. There's no need to do anything unique at all. On the left-hand side, you can see the transistor that show the transistor in FDSOI, and the two graphs at the bottom are just showing how, based on changing the through a forward body bias capability or a reverse body bias capability, you can either increase the VT of the device, i.e. slowing it down, but reducing the leakage of the device, and or you can lower the VT of the device, boosting the performance while at more power, but then you can immediately throttle that back down again. So you can get power when you need it, or you can really put it into that low power mode when you need it. Like I said, on the right-hand side, FD-SOI transistors are fully characterized and modeled with body bias. That includes digital, analog, RF millimeter wave. We have raw reliability qualification, and these are P cells with the body bias node already built in. We also readily support analog RF and millimeter wave with body bias. No extra PDK's enablement is required to get into those frequency ranges. And here at GF, we have created reference designs available for customers, complete with schematic layout test benches, design review documents. We've taken that all the way to silicon so customers can figure out how to best optimize body bias for a number of their circuits. This would be power amplifiers, ADCs and DACs, et cetera, just to name a few of those reference designs. And then finally, FD-SOI lays a solid foundation for the industry's first ecosystem of IP and solutions for digital designs enabling body bias, and Synopsys is one of our key partners in that. So let me talk about the ecosystem again, which I stated was off the shelf with Synopsys solutions. Synopsys is one of our key partners. Another is Dolphin. If we start from the bottom of this chart and work your way up, Foundation IP, Dolphin has adaptive body bias controllers as well as subsystems that they have available as part of their Foundation IP. And then Synopsys brings in standard cells, memories, IOs, PVT monitors, OTP memory as well to integrate into your design. Then moving up, you get to the design methodology. There is a full design methodology that both GlobalFoundries and Dolphin have created around the leveraging of body bias capabilities, and Synopsys has a full reference design flow as well that they're going to talk more about in this presentation. And then finally at the top, customers are adopting this. We have numerous customers who are using adaptive body bias. It is something that you need to design in from the ground floor of your architecture, but by taking advantage of it, you can really create best-in-class power performance with this solution. So now I'm going to turn it over to Synopsys to take you through the rest of the presentation. Thank you for your time.
Thank you, Dan, for the introduction to GlobalFoundries 22FDX technology and for highlighting the benefits and advantages of having body bias. My name is Severo Torres, and I'm an applications engineer from Synopsys, and I support IC Compiler 2 and Fusion Compiler. For my part in this webinar, I will be talking about the digital implementation of the ABB design, and I will have a demo to show later on to illustrate how you can implement a design using ABB technology. First, let's have a look at the broad portfolio of Foundry-sponsored Synopsys Foundation IP available for GF22FDX technology. This offering includes high-speed, high-density, and low-power standard cells, SRAMs, register files, ROMs, power optimization kits, GPIO, and specialty IOs. Options are also available for overdrive and low voltage, bias voltage BBTs, ultra-high density SRAMs, multi-channel length cells, and memory BIST and repair. This silicon-proven portfolio also includes automotive-grade memories and logic libraries. All of the libraries shown here support PVTV corners, except the ULL libraries. GlobalFoundries has a reference flow that includes the complete Synopsys design platform. This is a silicon-proven foundry flow that encompasses data preparation, through implementation, all the way to analysis, and then finally, physical verification sign-off. The tools that I want to highlight throughout the flow are as follows. For NDM preparation, you can use IC Compiler 2 to characterize the cells, the physical representation of them that the place and route tool will use. Synthesis, we have Design Compiler Graphical NXT. Formal verification can be performed using Formality and VCP LP. Design planning and place and route can be done using IC Compiler 2. And within IC Compiler 2, there is the InDesign capability to perform DRC and fill using IC Validator. Parasitic extraction and static timing analysis are done by StarRC and PrimeTime respectively. Lastly, for physical verification sign-off, DRC, LVS, and fill are done through IC Validator. The implementation phase contains 4 areas. First is the synthesis and DFT. Second, design planning. Next is the PNR optimization. And lastly, chip finishing. All of the tools that we have in Synopsys have access to all of the timing, power, multi-voltage, and test and formal verification analysis that's available throughout the flow. And we will demonstrate those tools as we go over the demo later on. On this slide, you see the complete digital implementation flow. It starts with design planning, synthesis, and place and route. And then you go through the sign-off, physical extraction, and static timing analysis. And lastly, physical verification. When you implement a design with body bias, you essentially use the same design flow and EDA tools, as mentioned before. There are no unique EDA tools that's required or extra number of sign-off corners that's needed. However, you do need specific information that is required. At the design planning phase, you need the body bias domains defined so that the design planning tool can identify which areas to put which cells in. Second, the library has to be characterized properly. It has to include the POCV and LVF with body bias information. And then during the implementation phase, the UPF connectivity and the PVTB corners have to be defined appropriately. Throughout the implementation phase, the design is going to be bias aware, such that certain things like tap cell connections or insertions are done automatically and identified the tool. Lastly, for sign-off, all of the corners with body bias have to be defined. Here is a rough block diagram of the design that we're going to have for the demo. There are 3 main components. First is a distributed timing monitor, or DTM for short, which provides timing information about the impact of the current PVT variations at performance. Second is an ABB core that generates the required body bias voltages, in this case through VNW and VPW, in order to compensate for the PVT variations that the DTM is monitoring. Lastly, there's an application design which we will be implementing hierarchically. It is a CPU in this case that talks both to the ABB core as well as the DTM modules. Here's a description of the test case that we have. For the block level, it is an OpenRISC 1200. It's a 32-bit scalar processor with Harvard microarchitecture. As I mentioned before, it's a hierarchical test case. We have 2 Dolphin design ABB IP. First is the ABB core, and then second, we have 2 different versions of the distributed timing monitors, or DTM. And lastly, the standard cell that we use is a DesignWare 7.5 track standard cell library. It's based on GF22FDX 1.3_2.0 PDK. Here's a much more detailed block diagram of the design that we will tackle during the demo. For the top level, we will call it OR1200 top, and the whole top level essentially operates under zero bias. the block level, which in this case is the OR 1200 CPU QMEM wrapper, is going to operate within the adapted body bias domain. There are two other hard macros, as mentioned earlier. There's the ABB core and then two DTMs. If you look at the block diagram, you will see that the VDD CPU is a shutdown voltage source that supplies voltage to the CPU QMEM wrapper. There is a requirement that the DTM and then the application design, in this case the CPU, exist in the same voltage and bias domain. And we will talk about that in more detail during the demo. Let's talk in more detail now about the top level. The module name is OR 1200 top. It has two rail supplies, VDD at 0.8 volt and VDD CPU at 0.65 volt. VDD provides supply to the standard cells at the top level, while VDD CPU provides power supply to the ABB core, the DTMs, and the OR 1200 CPU block. The standard cells being used is a Synopsys ULP library 7.5 track, and we're using both the base library and the shift library. The ABB core is connected to the VDD CPU at 0.65 volt and the analog VDD at 1.8 volt, which is the high voltage in this case. There are level shifters that are needed and are inserted between the top level boundary and the ABB core. The distributed timing monitors, or DTM, there is a soft wrapper that is used to instantiate these two DTM modules. The DTMs are connected to VDD CPU at 0.65 volt, and they are connected to the same bias nets as the OR 1200 CPU QMEM wrapper. The DTM wrapper again is implemented in the top level domain at the voltage supply of 0.8 volt. Because of the difference between that voltage and the VDD CPU voltage, level shifters are inserted between the DTM and the logic of the DTM wrapper itself. Next, let's talk about the block level. The module name for the block level is OR 1200 CPU QMEM wrapper. It is a dual rail block. There's a VCS power supply operating at 0.8 volt. There's a VDD CPU operating at 0.65 volt. VCS supply is used to power the memory bit cell in the block level, while VDD CPU is controlled by the power gates and supplies the rest of the logic inside of the CPU. The standard cell library again is using Synopsys ULP 7.5 track library, and for the block level we are using the base library and the LPK or low power kit libraries. Some low power features at the block level are power gates for the VDD CPU, as well as retention flops in the OR 1200_WB MUX module within the block. There are two memories in the design. There are two different ones, difference in size. Both are high-performance single-port SRAM S1P. One's a 128 by 128, and the other one is a 64 by 32-bit memory. Next, I'd like to show you the tool versions that we used for the implementation. For Design Compiler NXT, we used 2020-09 SP5. IC Compiler, we used 2020-09 SP6. For Malady, we used 2020-09 SP5. Synopsys Milky Way, we used 2019.12 SP3. For StarRC, we used 2020-09 SP5. And for RC Validator, we use 2020-09 SP3-4. We will now move on to the demo part of the webinar. Next, we will proceed with the live demo of our test case. Here we have a layout view of the design. Let us briefly go over the important aspects of the top-level design. Then we will dive on into the block-level implementation and talk more about the details there. As mentioned before, the top level is called OR 1200 top. You can see from the layout that there are three main components. The CPU, or OR 1200 CPU QMEM wrapper, which is the application design that we are going to implement hierarchically. The two DTM modules that are of different sizes. And then the ABB core. Next, let's talk about the power supplies at the top level. As mentioned during the presentation, we have the main power supply at the top level, which is VDD at 0.8 volt. You can see here the mesh for VDD power supply at the top level. Notice that this only goes into the top level and not into the modules like the DTM or the ABB core or the OR 1200 CPU. The power supplies for these other modules are the VDD CPU. Here's a mesh of the VDD CPU. You can see that at the top level, it's a lot more sparse than the VDD power supply. And you can see here that there are numerous tap points going into the DTMs, the ABB core, as well as the OR 1200 CPU. Once we dive into the CPU later on at the block level, I'll show you the mesh that's created internal to that. Also notice that there are rings around all of these modules at the top level to isolate the VDD CPU power supply. Next, let us talk about how the bias networks are created at the top level. At the top level, there are two bias nets, Net Bias 1 VNW and Net Bias 1 VPW. Here I've highlighted them, and you can see that the bias nets completely surround the ABB core, the two DTM modules, as well as the CPU application. Notice that there's only one connection or a pair of connections coming from the ABB core going to the rings that surround the CPU as well as the DTMs. These are signals supplied externally from the design, represented by these ports. You can see that there are numerous tap points from these bias rings going into these top-level modules. There's some tap connections here for the ABB core, as well on the other side, and internally they connect to these macros. Similarly, for the DTM modules, you see some tap points internal to these. And for the CPU itself, there are multiple tap points that go into the CPU at the block level. Here's one of them. There's quite a few on the lower corners of this design and the lower bottom of this design. These are what supply the bias nets internal to these modules. From the presentation, we talked about the usage of level shifters. Since it's important to have them up on the top level because of the differences in voltage. Remember that the top level operates at 0.8 volt and the modules operate at 0.65 volt. The level shifters I would highlight right now. You could see their close proximity to the ports or pins of these top level modules, and they sit pretty much adjacent to those pins just outside of their bounding box. I've used a routine where I've magnet placed these level shifters so that they get first priority for the connection to the ports and pins that they drive to and from the modules. I also want to note the location of the CPU wrapper, as well as the DTMs. In the presentation, there was a requirement that the CPU or the DTMs should be close in proximity to the CPU and that they share the same well. By doing this kind of a floor plan, we can isolate and make sure that that requirement is met. How do we isolate and make sure that the wells are isolated for the CPU and the DTM modules away from the top level? Essentially, we have column and row cells that have been inserted that surrounds these modules. You could see here that the CPU as well as the DTM are all isolated by the same set or within the same set of boundary cells that surround both the CPU and the two DTMs on the left side. Similarly, ABB core has its own set of boundary cell isolation to have its own well. Internally, we will have to connect them properly to the correct power pin connections so that the standard cells internal to these boundaries get the proper voltages as well as the proper well connections. Now that we've discussed some of the main topics at the top level regarding the layout and some of the physical aspects of the power planning and physical only devices that are at the top level, as well as the floor plan, let's go look at the actual scripts that we use to run the top level. First, let's look at the script that runs synthesis at the top level. Here you can see the makefile that's being used to run synthesis. As we scroll through the makefile, you could see the target points where the makefile will end. Typically, we use the makefile all the way to the target, which is syn, which is at the end of this makefile. At the end of this makefile, once it's executed, it will generate the data that is needed for place and route. And you will get this trigger that it's passed that point and completed that step of the makefile. Similarly, once the synthesis is done, there is a similar makefile for the place and route to run with. It looks almost the same as the synthesis run script. However, there are different target points where the makefile will start, execute, and then end. So once we've generated the data from synthesis, we will run this makefile for place and route in ICC2. And you could see the multiple steps in the place and route flow, starting from init design, which initializes the design. And also at this step is where the floor planning is created. After that step, we go through the placement and placement optimization. The target is placed opt, and then it goes through the couple of steps of clock op CTS and clock op opto. Clock op opto is the post CTS step where you optimize based on the data that you get once the clock tree has been inserted. And then after that, we go through the route and route optimization steps. You have route auto, which does the detail routing, global route, track assignment, and detail routing, and some incremental routing. And then you have the route op step, which basically does the optimization for timing once the detail routes are in place. For this particular test case, we ran this all the way to write data, where we're able to generate the data that is needed for star RC, as well as ICV, and data that's needed for formal verification. Next, the makefile scripts that I showed you both for synthesis and place and route are called by an actual run script that executes those makefiles. Here we look at the synthesis run script. It's essentially calling the makefile, make-f, calling the makefile file name, makefile DC for synthesis, and it gives you the target. So here it's going to generate all of the runs and information and data that is required for place and route. Alternatively, or similarly, we also have the same a similar run script for place and route. And here you see the same structure where you call make-f, the makefile script. In this case, the makefile is specific to PNR, make_file_PNR. And you see that the end target is going all the way to write data, which means that I'm going to use the data that I got from synthesis and then run through the whole entirety of the place and route steps, from initializing the design, placement and routing, and clock tree, and then generation of data. At the end of it all, you will end up with a directory structure that looks like this. When you download the RFL flow from Global Foundries, there will be a directory structure that has a scripts block where all of the scripts, both for synthesis and place and route, reside. There's an RMDC directory where the actual synthesis run is done. And then there's an RMICC2 directory where the place and route tasks are performed. And in those respective directories, you have a reports directory and the output directory that is needed to view the results from your run. Let's look quickly inside the RMDC directory. Here you could see 4 directories: logs, RPT for the reports, logs for the log files. Work is where the design library reside, basically where all the data of your run gets created. And then there's a temp directory that basically does the checkpointing for the makefile script execution. Similarly, for ICC2 run, we have RMICC2 directory that has the same directory structure where you get the same 4 directories: reports, logs, work, and TMP or temp directory. One of the important inputs for this run is the UPF. So let's take a look at the UPF for the top level. Here we call the UPF OR1200 underscore top dot UPF to signify that this is for top level. You could see that there are a bunch of information here that basically defines the supplies, the power domains. What I want to draw your attention to are the power domains that are created at the top level. There are three main power domains that are at the top level. First is PD top, which is the primary power supply at the top level. Then we have a power domain for the DTMs, call it PD ABB DTM. You could see that it takes two elements, and for those element inputs, we are giving them the names of the DTM modules. And then the next power domain is the ABB core, called PD ABB core. Notice that there aren't any power domains at the top level for the CPU module that we're implementing hierarchically. There's really no need for that because we are implementing it as a hierarchical block, and it's going to come up on top as an abstraction model. Next, let's talk about the power supplies that are defined for each of these power domains. You could see here power supply BDD. You could also see here the net bias nets, net bias VNW, and net bias VPW. Remember that these are the bias nets that get into the module, the CPU module. You could also see some of the high voltage nets, which are AVDD ABB and AVSS ABB, that basically supplies the 1.8 volt for the ABB core. And then lastly, you see a VDD CPU, which we have talked about earlier as the main supply that goes into the DTM, the ABB core, as well as the OR1200 CPU. Some other important aspects of the UPF at the top level are the definitions of the level shifters. Here you could see that we're defining a specific set of level shifters for the ABB DTM, as well as the ABB core and the CPU. Also, since there are a need for isolation cells at the top level, we also have to define an isolation strategy. And in the top level, we have two. One defining the isolation for the QMEM wrapper, or the OR1200 CPU. And then the other one the isolation strategy for a clamp value of 1 for the OR1200 CPU. Those are basically the main items that I wanted to cover regarding the UPF for the top level. What we would do now is go into the block level and then discuss the important details that we need to do. Please keep in mind that for this flow, we actually did a bottom-up approach, where we first synthesize the block level, in this case the OR1200 CPU QMEM wrapper, and then created an abstraction model for that, which we then instantiated at the top level. And when we implemented the top level, the CPU module comes in as an abstraction model. And all of the optimizations are run about that model. Let us now dive in to the block level. In this case, it's called OR1200 CPU QMEM wrapper. First, let's look at the layout. You can see from the layout that there are two components inside of here. And these are the single port memories that we mentioned earlier during the presentation. On the left side is this 128 by 128 single port memory, and on the right side is a smaller 64 by 32 single port memory. These memories are powered by the VCS voltage source in the block level. Here I've created a mesh and made sure that they would cover the entirety of these memories. You could see if I zoom in that there are tap points from these straps that go into the pins of these memories. For instance, there's a VCS pin here where the actual strap goes connect to internally. Next, let's talk about how the VDD power supply gets propagated down into this CPU module. From the top level, we have the VDD net, which powers the power gates. You can see that I've created a mesh for the VDD net as well. However, I'd like to draw your attention to the wide metals that are sitting directly on top of the power gates. You can see that the VDD net that sits on top of the power gates are quite wide. They're about 4 microns wide. And you could also see that the power gates are arranged in a staggered fashion so that we get good coverage once we are able to shut down the entire block. So from this top level VDD power supply, these power gates would power the internal supply, which is VDD SD, inside of the CPU module. And the net again is called VDD SD, short for VDD shutdown. And you can see here that from the power gates, the VDD supplies these pins. You get an enable signal for this if the block is on, and then disable it when it's off. And then this basically becomes the main supply for the block level. You can see that there's a mesh for this as well as the actual rail connections. The power gates are called header blocks, and this is basically what they look like. They are arranged in 3 columns, just enough to cover this size of a block. Next, how are the bias nets propagated into this CPU module? Remember that we have net bias VPW and net bias VNW nets that are coming from the top level. In the block level, they are called VNW, net bias VNW, and net bias VPW. You could see here that I have quite a bit of a dense mesh that sits directly on top of the memories. I had to do this because there are bias pins on these memories that need to be supplied these nets. So it's somewhat custom made and made sure that it overlaps or sits on top of these memories. The other aspect of it is, I'd like to show you that these bias nets also drive the tap cells. And from these tap cells, this is essentially how the bias nets get propagated into the well of this CPU module. So here you'll see bias nets VPW and VNW supplying the tap cell, and then the tap cell now supplies the net bias for the entirety of this block. The top cell should have complete coverage on this entire block. Let's zoom in real quick and look at the tab cells. You can see that they're about a regularity of 35 microns apart. The other low voltage feature of this block level is the existence of retention flops. Here I highlight for you the retention flops that are included in this design. Now that we've talked about the important components of the OR1200 CPU QMEM wrapper, let's look at the scripts that actually are ran in order to implement this block level. Just like the top level, there's a makefile for DC and a makefile for the PNR, or place and route. Let's quickly look at the makefile for synthesis. As you can see, it's pretty similar to the top level. It has the same targets, export to PNR. And similarly, for the place and route, we have the same similar structure as the top level, starting from init design all the way to write data. And the run script that creates them are essentially the same as the top level, or similar. There's a run syn and a run PNR script that are run at the block level. Let's look at the UPF for the block level. Here in the block level, you'll see the power domains. For this module, there's only one power domain, which is PD OR1200 CPU QMEM wrapper. And you can also see the different power supplies that we've talked about earlier. VDD, BCS, the bias nets, BNW and VPW, as well as the VDD SD, which is the shutdown voltage. During the presentation, we've talked about a couple of the low power features for this block level. First is the power switch, or the power gates. And here you have the definition on how these power switches are created and instantiated. Create power switch, and then map power switch commands are in the UPF. And here you see the cells that are being used in order to implement the switches. Next are the retention register information. From the presentation also, if you remember, the retention registers are all in the OR1200W MUX module. Here we're telling it what the retention information is, and then the retention control, and then how we map which cells to use for the retention registers. Here we're using these RET2 CSDFFQ retention cells. That is essentially what I'd like to show on the UPF file for the block level. One of the main things that we wanted to ensure with this webinar is to show you how easy it is to use the ABB technology in any design. Once your design is fully set up, if you go into your setup directory where you have the Synopsys_PNR directory, you will have the scripts called run syn and run PNR. For synthesis, it's as simple as running run syn. We will do that right now. And that will farm off a job to finish the synthesis part of the flow. Once the synthesis part is done, then you will go back to this directory and run PNR C shell. So that would spawn off the jobs that's needed to complete the PNR run. Let's look at some of the results from the block level run. Under the SNPS PNR directory, you will see the directories for synthesis, RMDC, and for PNR, RMICC2. For synthesis, all of the information are in this directory. You have the logs from your synthesis run. Notice we're using the version 2020-09 SP5 for synthesis. And if you look at the bottom of this log file, you'll see that the synthesis for the block level took about 4.92 hours, or an elapsed time of 3.84 hours. Similarly, for the PNR results, you go to the RMICC2 directory, and there you will see a log directory. And let's just look at the last implementation step, which is route opt. This is the log file for the last step of place and route, which is route opt.log. And here you see that we use 2020-09 SP6. And for the route opt step, which is the last step in PNR, it took about 1.29 hours of elapsed wall clock time. The data that are generated as a result of the complete PNR run is going to be stored under the work directory. And there's a write directory in here. And here you will see all of the generated outputs from your run. You'll see the LVS netlist. You'll see the formality netlists that are needed. You see what's needed for VCLP. You also see the final output UPF. And also the final def. And all of the scenario-specific SPEF information that's needed for sign-off timing analysis, as well as all of the SDCs for all the different modes that were ran. And of course, you'll have the final GDS file that you can now bring to ICV for sign-off physical verification. So once the block level is done, you are now free to move to the top level and then do the same steps as you did in the block level, essentially run synthesis and PNR. Remember that we did a bottom-up approach where we implemented the block level first and then instantiated a model of that at the top level, and then implemented the top level through synthesis and PNR. So here's the layout of the complete design. I'm going to enable all of the visibility switches here so that you could see everything, the final product of the design. Here it is with all of the power supplies, power meshes and such. It is a completely filled design, meaning all of the filler cells have been inserted. You could see them all in there. Also, this is a fully routed design, and you can see that the signal routes are all in there, as well as the clock routes that are present as you zoom in. The cool thing about the top level is that you could actually dive into the block level and see what's inside, since this is carried to the top level as an abstraction. You could look at the abstract model of the design and see what it is that's being passed at the top level during optimization. This is not the complete net list. However, you could also expand it as if it's a complete design, at which point you have the complete, fully implemented block level. You can see that the routings are all in here as you zoom in further. So that concludes our demo for the ABB demystification project. I hope you enjoyed it and learned something from it. The key thing to remember is that it is an easy task to include ABB into your design. In summary, we have covered adaptive body bias and the benefits. We have also covered the GlobalFoundries 22 FDX reference flow using the Synopsys platform. And we have demonstrated in a test case how to enable the ABB feature in your design with some small changes. I hope that this training is beneficial, and hopefully the next chip you design will have an ABB in it. Thank you very much. And thank you to all that contributed to this webinar. Goodbye.